All right, our next speaker will be Samuel Varner. He did his practicum at Argonne National Laboratory and is studying chemical engineering at the California Institute of Technology.
All right, thank you. Thank you so much. Thank you everyone for being here for these morning talks. So far they've been extremely interesting and very diverse as well, and I'm going to add to that and completely change topics, I think, and kind of show hopefully an example of how the CSGF can impact someone like me who's really doing basic science and not doing sort of this hardcore computer science, machine learning, which is so interesting, but I'm doing polymer physics, and in a group, Professor Zhenggang Wang at Caltech, who largely built his career just doing pen and paper theory, but the CSGF, through me and through Chris Balzer, many of you probably know, has kind of transformed what this group has been able to do. And yeah, I'm hoping to show just a project I picked up over the past 6 months, and something I find very interesting. So I'm going to be talking about block copolymer micelles, and first I want to introduce what block copolymers are, because most people here probably aren't in polymer physics, but block copolymers are just basically exactly what they sound like. If you take two polymers, usually synthetic polymers, and you link them together, you have a block copolymer. So a classical example of that is polystyrene blocked with polymethyl methacrylate, and generally if you mix these polymers in a melt, not in their block structure, but you mix them in a melt, they'll macro phase separate because they're incompatible polymers. But what becomes interesting in the block copolymer case is now the incompatible things are connected. So they can't macro phase separate from each other anymore, and you get something called micro phase separation, where it phase separates on a nanoscopic length scale rather than a macro scale. In the context of solutions of block copolymers, you have polymers immersed in a selective solvent, and so in the polymer physics community, we call the block that forms the center of the micelle the core block, the block that forms the outside of the micelle the corona block, and then the solvent is a selective solvent. So if you have a polar solvent, then your core block is going to be hydrophobic, and your shell block or corona block is hydrophobic. And depending on the relative size of the two blocks, you can get different structures. For example, spheres, cylinders, and in the extreme case of a very long core and a short corona like a phospholipid, you get membranes and vesicles. Okay, so we'd like to be able to understand how we form micelles of a particular size and of a particular distribution, which is sort of a classical problem for surfactants, is if you know the architecture and the type of surfactant you have, how can you predict what kind of micelles you're going to form and at what concentrations, and are they going to be stable under certain conditions, which has obviously huge implications for consumer products. But in the block copolymer case, it's a little bit different because we have these very long, high molecular weight synthetic polymers. The process proceeds through 2 steps. So there's a first step where you have chains dispersed in a solution, and then they quickly aggregate into these small clusters. And then there's a second step, once all the free chains are exhausted, where these small clusters need to equilibrate to reach their actual thermodynamic equilibrium distribution, which is not this middle picture, but is this final picture. And there's a red X here to indicate that that process is very slow, and so you're often kinetically trapped in this state of unpredictable and polydispersed micelle sizes, which is not where we want to be. So in general, we want to be able to leverage thermodynamic equilibrium states because they are predictable, and you don't have to put much energy or effort into your system generally to get something to progress towards its thermodynamic equilibrium. That just doesn't happen to be the case for block copolymer micelles. So I want to further explain that through the context of the actual method that people use to fabricate these micelles called co-solvent-assisted dissolution. So what this process is you start with a solution of polymers in a co-solvent. So the solvent basically doesn't prefer to solvate either the core or the corona preferentially, but it solvates both, and so you get a dispersed solution of polymers, and then over time you slowly add selective solvent in, so you titrate a selective solvent in and you start forming micelles once there's enough selective solvent in the system. And then you start forming these aggregates, and over time, all the free chains get enveloped into these small aggregates, and you run out and you get this distribution at time tau star, say. And this is a fast process because generally you're at conditions well above the critical micelle concentration, so the initial aggregation barrier is very low, and you wind up at this point here. And just looking at this sort of free energy curve here, the equilibrium is this minimum, and you might be thinking, well, it should be very easy to slide down this very steep minimum, very steep pathway to get to this thermodynamic equilibrium here at a much larger aggregation number. But this picture doesn't include any information about the actual mechanisms to get from this distribution to the next equilibrium distribution. And so a more accurate picture will include the barriers that you need to overcome to actually reach that minimum, and that's through the different equilibration mechanisms that exist. So there's the chain exchange mechanism, so a chain can hop out of a micelle, diffuse, and enter another micelle. And there's also fusion and fission, where say for example in the case of fusion, two smaller micelles can find each other in the solution and fuse into a larger micelle. And so if I incorporate that now into the picture, we still have that initial association, which has a very low free energy barrier, and then we get stuck after a certain point because we have no more free chains to help us increase our micelle sizes. And so we have a lot of this very rugged landscape where we need to overcome this same large free energy barrier many times to get to the true equilibrium. So we have a puzzle here of trying to overcome this inherent kinetic trap in block copolymer micelles to be able to get to the equilibrium and achieve consistent and predictable micelle size distributions that are stable to thermal changes and will be actually applicable for things like drug delivery and nanoreaction. So I set out to try to help some experimentalists that I'm working with determine what's going on in an alternative route and how we can better control what the final micelle size is. And that is through this alternative method, which we call the direct dissolution method. And so basically the difference here is we're starting from a different starting point. Instead of starting with a solution of block copolymers in a co-solvent, we just start from a block copolymer in the melt state. And generally it will already be in its microphase separated state, which will be, in the case of a nearly symmetric block copolymer, it will be a lamellar thin film. So you start with the lamellar thin film, and then you directly, hence the name direct dissolution, dissolve it in the selective solvent. So at this point, when you introduce the selective solvent, it will rush into the block that it prefers, which is going to become the corona block of our eventual micelles, and cause it to swell, which causes this lamellar phase to become unstable, because now you have this geometric shift due to the swelling. And then after some time, what they find is that they get this distribution of micelles that are relatively monodispersed, and they're a lot larger than the micelles that they're able to get from the other method. And so the question then that I set out, when I heard this, they were talking about this at a conference, and I just said, well, I think I can simulate this and get a better picture of what's going on between this and this. So basically unraveling what is going on in this arrow, because they really have no idea. So to study this, I appealed to molecular dynamics simulations, and it might not be the type of molecular dynamics simulations that a lot of people here are familiar with, because we're looking at phase separation behavior of these high molecular weight polymers on the mesoscale. So it's between tens and hundreds or thousands of nanometers that these phenomena are occurring. And so what we do is we take advantage of the fact that polymers have a very natural way of coarse graining. Right? Polymers are just random walks. And if you take a subsection of a long random walk, that's also a random walk. And we know statistically what the distribution of the distance that random walk will travel over a certain number of steps should be. It's a Gaussian distribution. So that naturally gives us a potential for this sort of new sort of pseudopolymer that we have here, where these endpoints of the polymer are connected by harmonic bonds. So harmonic bonds would give us a Gaussian end-to-end distance distribution. So we just take our long polymer and group it into these subpolymers, and we call these super bonds, where we're connecting now these new monomers which group many polymer subunits into them, and we have them connected by this harmonic bond. And because we're grouping together many polymer units in one monomer, we lose that atomistic detail, and there's no longer any hardcore repulsion in our system. And so we're able to utilize any repulsive soft core potential to describe the fact that these segments in general don't want to overlap, but there's no direct hardcore repulsion, which allows us to extend simulations to a much larger length scale and longer time scale, because we can have much larger time steps and much less particles in the actual simulation. So this is generally used a lot in the soft matter community for studying these large systems of polymers. And the main thing to note here about the parameters, well, it's not so important what the exact numbers, is to note that the core block dislikes the solvent more than the corona block, which is how we're going to form micelles in the end. The integration scheme that we use for these simulations is a very popular one. If you're in the soft matter community, you'll have heard of it before, dissipative particle dynamics. The main thing to note with this is that it includes hydrodynamics, whereas something like a Langevin integrator does not. And so it's not the best way you can include hydrodynamics in molecular dynamic simulations, but it's better than nothing, and it's also relatively cheap compared to other methods. So I want to talk a little bit about how I actually go about the simulations, and I do that by starting with the polymers dispersed, and this slide I'm going to show how I get to the initial state of the experiment, because it's kind of a hard initial state to do in a simulation, but the way I did it was by putting the chains in the box, and here I'm deleting the solvent from the picture just so we can see the polymers a lot more clearly. But I start with the polymers dissolved in the solvent, and I drag them to the center. And right now, both blocks dislike the solvent, and this allows me to form a thin film that's sandwiched in between two layers of a non-solvent, and then I release that dragging force, and I get a lamellar thin film that's sandwiched in between two layers of non-solvent. And this is basically my starting point. They have a thin film that's exposed to air or a vacuum, and I have this thin film that's sandwiched between non-solvent, which is essentially air, right? And then that's going to be the starting point. I'll instantaneously swap out that non-solvent for the selective solvent. It will rush into the corona block, cause an instability, and we'll go from that to micelles somehow. And one thing I want to note is we're in what's called the star-like micelle regime here, which means that the most favorable state is a spherical micelle, but we're going to see that the system passes through another state that's non-spherical on its way to the spherical state. And another thing I wanted to note is that these simulations, each simulation has around 1 million particles, which to most people in this room maybe doesn't sound like a lot, but it becomes a little bit more impressive when you realize I can run this simulation within 1 to 2 days on 2 generations back NVIDIA hardware, consumer hardware, which means I can run the entirety of the work for this. If I write good HPC code and write good code to interface with the schedulers on HPC and things like that, I can do all of the calculations for this work within 1 to 2 weeks. So, I mean, that for me is a huge win. And one of the main things I took out of being in the CSGF is how to utilize those resources to automate all of my work out and not having to do anything manually. So I'm going to run this, and here I'm coloring the polymers according to which cluster they belong to, and I've deleted the corona block now so we can really focus on the core of the micelles. And so we'll see that there's an instability when the solvent starts entering, and these lamellae form finger-like structures which turn into cylinders. And then those cylinders extend, and over time, because the cylinders are unstable in this regime, they pinch off and form these relatively monodispersed micelles. If I compare that to the co-solvent assisted method, I start with these polymers dispersed in a co-solvent, and I swap it for a selective solvent. We see we have that initial aggregation where the number of micelles is increasing initially, and then we exhaust all the free chains. So we're not getting any more micelles, but micelles are starting to fuse together. So the number of micelles starts decreasing while the average size of the micelles is increasing. And the main thing to note with this is that after that initial aggregation, which is about at this T over T naught equals 100, the process slows down magnificently because of the strong barriers that I mentioned to the fusion and the exchange process. So this coarsening behavior is much, much slower than traditional coarsening you expect in phase separation processes from like Kahn-Hilliard or something like that. Okay, I will wrap up in hopefully 1 minute and then have time for questions. And so if I plot then the average aggregation number of the micelles I get from the two different methods, we see that the micelles starting from the ordered thin film state are on average 2 times or greater than the micelles from the other state. And we wanted to see if this was close to equilibrium or not, so we had to appeal to statistical mechanics and use something called polymer self-consistent field theory. And this is sort of the other thrust of how the CSGF really impacted me. I had to write all of my own numerical solvers from scratch, which is basically, in this context, solving fixed point iteration problems for millions of equations, millions of nonlinear equations, including differential equations in there as well. And so I learned how to write in CUDA and parallelize everything as much as possible to be able to do this, which was able to allow me to do a lot more work in my PhD than other grad students in my group and other groups as well. But the main output of this is that you can get density profiles, which you can then use to compute the free energy through a free energy functional. And we saw that the results that we got were from the SCFT showed that we're very close to equilibrium. Our micelles are very close to the equilibrium size when we go through the direct dissolution as opposed to the co-solvent assisted dissolution. And with that, I want to make sure that I thank, there's so many people missing from this slide, unfortunately, but my advisor for allowing me to take full use of the CSGF and basically do whatever I wanted during my PhD. He never imposed anything on me, which was very nice. Thank my experimental collaborators, Kyle at Argonne for being an amazing practicum coordinator and just making that the easiest process ever for me. My advisor at Argonne, Juan, who I most likely am going to go work for as a postdoc when I graduate, and also Chris, who many people in this room probably know. He's the one who influenced me to apply for the fellowship, and I learned most of the things I know directly from him, so he's great. And with that, I'll take questions. Thank you.